Hello. Hello and welcome to this video on Rust programming. We are not going to write any code. We are going to go through the documentation of vector. It is found in collections. So if you don't know how to reach here, you simply Google std collections Rust and you will land up here. Once you are here, you click vector. Okay. So first of all, let me explain why we are doing this. The reason is twofold. One is that we want to know what we can do with vectors. And the second is that it is a good idea to go through documentation repeatedly. Even if you have read the documentation and you know everything, once in 3 months or 4 months, or perhaps with every release, you should go and check the documentation so that you can update your knowledge about the data structure or whatever functionality the library is providing. So vector is a mighty useful data structure, very useful. Okay. As you know, we have talked a lot about vectors. We have used it. So a vector is basically a contiguous growable array type, written as vecti, short for vector. It is there in almost all programming languages with the possible exception of C. So an equivalent will be there in Python. We have list. In C++, we have vector. I don't know what Java has. The JavaScript has the array. Okay, it can grow for as long as you need. And what other programming language I code in? Lists are there in scheme and list. You can append as many items as you need. And almost all languages will have something equivalent. So usually you want to create a mutable vector unless you are initializing it with data. So this is how you create it, and you push the elements. They are appended at the end. At this moment, the length will be 2 and 0th item will be 1. So it is an indexed data structure. You can access elements by index. You can pop and it will return an option enum. So sum2 will be the output because 2 was the last element. So pop will pop from the end and vector length will be 1. You can assign at an index. 0 is valid right now, so we can assign 7 and that 0 will be 7. Extend will add more elements, 1, 2, 3 at the end, and if you print this, it will print 7, 1, 2, 3, and we can do an assert for equality as well. So here we created using the function new, and here we are using the macro for convenient initialization. We create a vector with elements 1, 2, 3, we push 4. And then we have vector 1, 2, 3, 4 here, or we can call from as well to initialize a vector. We can simply put the data here and note the syntax. It is brackets, square brackets, okay, everywhere. All right. In C, it is brace. We don't use brace for vectors in Rust. For C, the array would have brace. Okay. Now we can also initialize all elements of the array with a given value. So 0 is here and semicolon followed by count. So get 5 zeros, and you can do with capacity as well with 5, and you decide 5 to 5 zeros here. So you get 0. Okay. Now vector is an efficient stack, so you can push data here. We call it stack. The variable name is stack, and then you can pop. Now you can access the elements by index because it implements index trait. So here we have 0, 2, 4, 6, and V1 will give 2. Then if you try to access out of bounds, compiler will not check this for you. It will be a problem at runtime, and it will be basically a panic situation. Use get and get mut if you want to check whether the index is in vec. So get and get mut are safe. A vector can be mutable. On the other hand, slices are read-only objects. To get a slice, use ampersand. So read slice, it takes an argument of a slice of usize. I'll explain usize in a moment. So vector 0, 1 is there, and we sent it vector as a reference with variable, and it is treated as slice. So the significance of usize is that the length, if you see here, where we use length, yeah. So this length, what it returns is 2. But what is the type of 2 here? It is usize. Okay. Usize is basically equivalent to long end in C or C++. Essentially, usize represents the size of the pointer. So in C, C++, it is really size underscore t, which is a type to unsigned long. Okay. So on 64-bit systems, this usize would be 64-bit, and it can represent values up to 2 to the power 64 minus 1. And in C, C++, the same thing would be size underscore t. Okay. And the other way you can write it like this. In Rust, it is more common to pass slices as arguments rather than vectors when you just want to provide read access. The same goes for string and &str, because string is essentially a vector of U8. Now here is some information about capacity and relocation, which you will read. The capacity of a vector is the amount of space allocated for any future elements that will be added onto the vector. This is not to be confused with the length of vector, which specifies the number of actual elements within the vector. If a vector length exceeds its capacity will automatically be increased, but its elements will have to be reallocated. For example, a vector with capacity 10 and length 0 would be an empty vector with a space for 10 more elements. Pushing 10 or fewer elements onto the vector will not change its capacity or cause reallocation to upper. However, if the vector's length is increased to 11, it will have to reallocate, which can be slow. For this reason, it is recommended to use vec with capacity whenever possible to specify how big the vector is expected to get. Now we have some guarantees. Due to its incredibly fundamental nature, vec makes a lot of guarantees about its design. This ensures that it is as low override as possible in the general case, and can be correctly manipulated in primitive ways by unsafe code. Note that these guarantees refer to an unqualified vec-t. If additional type parameters are added, example to support custom allocators, overriding their defaults may change this behavior. Most fundamentally, vec is and always will be a pointer capacity length triplet. No more, no less. The order of these fields is completely unspecified, and you should use the appropriate methods to modify these. The pointer will never be null, so this type is null pointer optimized. However, the pointer might not actually point to allocated memory. In particular, if you construct a vec with capacity 0 via vec new or vec with capacity 0, or by calling shrink to fit on an empty vec, it will not allocate memory. Similarly, if you store 0 size types inside a vector, it will not allocate space for them. Note that in this case, vec might not report a capacity of 0. Vec will allocate if and only if size of type t multiplied by capacity greater than 0. In general, vec's allocation details are very subtle. If you intend to allocate memory using a vec and use it for something else, either to pass to unsafe code or to build your own memory-backed collection, be sure to deallocate this memory by using some raw parts to recover the vec and then dropping it. If a vec has allocated memory, then the memory it points to is on the heap, as defined by the allocator Rust is configured to use by default, and its pointer points to len initialize. Contiguous elements in order, what you would see if you coerced it to a slice followed by capacity minus len logically uninitialize. Contiguous elements. A vector contains the elements A within the quotes and B within quotes with capacity 4 can be visualized as below. The top part is the vec struct. It contains a pointer to the heap of the allocation, head of the allocation in the heap, length and capacity. The bottom part is the allocation on heap, a contiguous memory block. So this is the pointer of the vector. Its length is 2 and capacity is 4. So we have allocated 2 elements here, A and B, and remaining two are uninitialized, and this is the memory in the heap. Uninit represents memory that is not initialized. C may be uninit. Note, the ABI is not stable and VEC makes no guarantees about its memory layout, including the order of fields. VEC will never perform a small optimization where elements are actually stored on the stack for two reasons. First reason is it would make it more difficult for unsafe code to correctly manipulate a VEC. The contents of a VEC wouldn't have a stable address if it were only moved, and it would be more difficult to determine if a VEC had actually allocated memory. It would penalize the memory space, encouraging an additional branch on every access. VEC will never automatically shrink itself even if completely empty. This ensures no unnecessary allocations or deallocations occur. Emptying a VEC and then filling it back up to the same length should incur no cost to the allocator. If you wish to free up unused memory, use shrink to fit or shrink to. Push and insert will never reallocate or allocate if the reported capacity is sufficient. Push and insert will reallocate if length is equal to capacity. That is, the reported capacity is completely accurate and can be relied on. It can even be used to manually free the memory allocated by a VEC if desired. Bulk insertion methods may reallocate even when not necessary. VEC does not guarantee any particular growth strategy when reallocating when full, nor when reserve is called. The current strategy is basic and it may provide desirable to use a non-constant growth factor. Whatever strategy is used will of course guarantee O1 amortized push. So O1 means the push will be always constant time. It is guaranteed in order to respect the intentions of the programmer that all vector of element of this type E1, E2 through En or X of n count and VEC with capacity n produce a VEC that requests an allocation of the exact size needed for precisely n elements from the allocated no other size, such as, for example, a size rounded up to the nearest power of 2. The allocator will return an allocation that is at least as large as requested, but it may be larger. It is guaranteed that the VEC capacity method returns a value that is at least the request capacity and not more than the allocated capacity. The method VEC shrink to fit will attempt to discard excess capacity an allocator has given to a VEC. If length is equal to capacity, then a VEC T can be converted to and from box T without reallocating or moving the elements. VEC exploits this fact as much as possible when implementing common conversions such as into box slice. VEC will not specifically overwrite any data that is removed from it, but also won't specifically preserve it. It is uninitialized memory is cache space that it may use however it wants. It will generally just do whatever is most efficient or otherwise easy to implement. Do not rely on removed data to be erased for security purposes. Even if you drop a VEC, its buffer may simply be reused by another allocation. Even if you zero a VEC's memory first, that might not actually happen because the optimizer does not consider this a side effect that must be preserved. There is one case which we will not break, however, using unsafe code to write to the excess capacity and then increasing the length to match is always valid. Currently, VEC does not guarantee the order in which elements are dropped. The order has changed in the past and may change again. So now we look at the functions. There are some functions here. One is new, which we have seen. It constructs a new empty vector. The vector will not allocate until the elements are pushed into it. Then we have with capacity, which will allocate with capacity. The vector will be able to hold at least capacity elements without relocating. This method is allowed to allocate for more elements than capacity. If capacity is 0, the vector will not allocate. It is important to note that although the return vector has minimum capacity specified, the vector will have a 0 length. For an explanation, we have seen capacity and reallocation section. It is important to know the exact allocated capacity of a VEC. Always use the capacity method after construction. So we have here capacity is 10, length is 0, capacity is greater or equal to 10. then we push elements, 10 elements, no reallocation will happen and length will become 10 and capacity will be greater than equal to 10. But if you push another element, it will cause vector to allocate, length will become 11, capacity will be greater than equal to 11. So if you allocate vector with 0 unit size, you will see that capacity is there and it will be will always over allocate, okay, and there'll be no memory given to it. All right, so capacity will be maximum of v size here. Then we have try with capacity, and it will try to create a new vector with that much size, and there might be another. The vector will be able to hold at least capacity elements without reallocating, so it's the same thing. Returns an error if the size capacity exceeds I size max bytes. So here there is a very important distinction we have. I size is not U size, okay, and this is the limitation we have. This is the maximum memory allocation it will do. So if you look at I size max rush, what it will be is, so let me show you. This is roughly this is KB, this is MB, this is GB, then we have terabytes, petabytes, exabytes, 9 exabytes. Okay, that is the maximum data you can allocate for a vector. Length is always U size. Okay, because if you allocate one element or rather 1 byte element, right? In the for example, U8 is 1 byte element. It can allocate up to 9 exa U8 elements in this. Okay, but the type is U size. The type is not I size. Okay, because the reason is length cannot be negative. So that's that. Okay. So from raw parts, takes a pointer, length and capacity, and you can create this. Okay. This is highly unsafe due to the number of invariants that are not checked. If a T is not a 0 size type and the capacity is non-zero, PTR must have been allocated using the global allocators such as via the alloc alloc function. If T is a 0 size type or capacity is 0, PTR only need to be non-null and aligned. T needs to have the same alignment as what PTR is allocated with. If the pointer is required to be allocated, T having a less strict alignment is not sufficient. The alignment really needs to be equal to satisfy the dealloc requirement that memory must be allocated and deallocated with the same layout. The size of T times capacity, that is the allocated size in bytes, if non-zero, needs to be the same size as the pointer was allocated with. Because similar to alignment, dealloc must be called with the same layout size. So here I will talk about alignment a bit. I believe in the past I have talked about alignment, but I'm not sure, I don't remember it. So what alignment basically says is that suppose there is a data type, okay, and it occupies n bytes, then its address will be such that that address is divisible by that n, okay. So if your data type occupies 1 byte, it can go to any address, it can end at anywhere. But for example, let's say integers, 32-bit integers use 4 bytes. So the boundary for them, that is the address where they will be allocated, will always be divisible by 4. So that is the requirement of alignment. But essentially what it means here is that the PTR and T, the type here, both should have same size. Okay, that should cover the alignment part. Okay, length must be less than or equal to capacity. The first length value must be properly initialized values of type T. Capacity needs to be the capacity that the pointer was allocated with, as the pointer is required to be allocated. The allocated size in bytes must no longer be no larger than I size max. See the safety documentation of pointer offset. These requirements are always upheld by any PTR that has been allocated via VecT. Other allocation sources are allowed if the invariants are upheld. Violating these may cause problems like corrupting the allocator's internal data structure. For example, it is normally not safe to build a vec U8 from a pointer to a C-char array with length, size, and score T. Doing so is only safe if the array was initially allocated by a vec or string. It is also not safe to build one from vec U16 and its length because the allocator cares about the alignment, and these two types have different alignments. The buffer was allocated with alignment 2 for U16, but after turning it into a vec U8, it will be deallocated with alignment 1. To avoid these issues, it is often preferable to do casting or transmitting slice from raw parts instead. The ownership of PTR is effectively transferred to the vec key, which may then deallocate, reallocate, or change the contents of memory pointed to by the pointer as well. Ensure that nothing else uses the pointer after calling this function. So we have vector here, and from raw parts we deconstruct, we get pointer, len, and capacity. And in the unsafe block, what we can do is we iterate over the length, we take every element and we add it to T, and we say 4 plus I. Okay, so we override 4, 5, 6 here. Okay, it is 1, 2, 3. So 3 was length, so I will be 1, 2, 3. So it will override 4, 5, 6. Now with 4, 5, 6. Now we rebuild from the T and we get 4, 5, 6 here. Now using memory that was allocated elsewhere. So this I will not talk about right now because we are not talking about allocate and layout. Then we have unsafe function. Unsafe I will skip for now because unsafe is some territory which we should not consider. Nightly API we are not going to study. Into raw parts we will not talk about into raw parts right now unless we have studied unsafe. Into parts, nightly API. We are not going to cover nightly API till they are stable. Then we have push. So push appends an element back to the collection. Okay, it does not return. Time complexity is O1. Push mutable returns ampersand appends an element back to the collection, back of a collection, returning a response to it. So panics if new capacity exceeds I size max. So you can do this, and time complexity is O1. Then we have new these are nightly API. We are not going to touch them. Nightly API. Okay. Then we have capacity. We have already seen this reserve. I think I'll stop here. Okay, we are at reserve. Where is that? Reserve. Okay, this is alphabetical. It is not alphabetical. So we'll stop here and we will continue with Rust vector in another video, or rather in the next video. There's quite a bit of ground we have to cover. There's lots of information here. So we'll stop here and I'll end this video. So I hope that you are enjoying this discussion. Okay, you can go to Rustlang and you can actually run these programs. Okay, when you put your mouse in the area cursor, you can run this. Okay, so it will open in playground and you simply say run and it will run it. Okay, so I hope that you are enjoying and finding it useful for learning Rust. So thanks a lot for watching the video, and I'll take my leave here and see you in the next video. So quit learning and have a nice day. Enjoy.